Hello everyone, welcome to ashatech.com, your engineering sciences channel. In this video, we are looking at the design of machine elements, and our discussion is going to be localized to shaft design. A shaft is supported on bearings A and B, 1000 mm between centers. A 22 degree straight tooth spar gear having 600 mm pitch diameter is located 300 mm and to the right of the left hand bearing A, and an 800 mm diameter pulley is mounted 300 mm towards the left of bearing B. The gear is driven by a pinion with a downward tangential force, while the pulley drives a horizontal belt having 180 degree angle of wrap. The pulley also serves a flywheel and weighs 2,500 newtons. The maximum belt tension is 3,000 newtons and the tension ratio is 3:1, meaning that the tight side has 3 and the slack side has 1. Determine the maximum bending moment and the necessary shaft diameter if the allowable shear stress of the material is 40 megapascals. It means here we are going to only utilize the maximum shear stress theorem, or what we call Tresca's theory, to design this particular shaft and get its dimensions. Now this is the transmission mechanism that we are looking at. We have a pulley here, we have a gear all fixed on the shaft that has to rotate on bearings A and B. The distances are indicated as given: 0.3 meters from A to C, then between C and D 0.4 meters, between B and D 0.3 meters. Now the diameter of the gear, we are given that the pitch diameter is 600 mm, and therefore radius, converting it to meters, would be 600 millimeter divided by 2, then I divide it by 1000, this would give me 0.3 meters. Then the diameter of the pulley is 800 millimeter divided by 2 divided by 1000, this would give me the radius of the pulley at D, giving me 0.4 meters. Then the weight of the pulley is also 2,500 newtons, and the maximum tension in the belt, if we call it T1, it will be 3,000 newtons. If I look at the whole system, it will be, I will have a shaft at the center, then I have a gear, then I have a pulley. So the pulley transmits power horizontally through the belt mechanism, then the gear receives the power through a pinion, and we are told that the tangential component of the normal force on the gear tooth is FTC and is acting vertically downwards. Something to note is that if T1 is a maximum tension in the belt, then that is the tight side of the belt, and also if T2 is the minimum tension, then that will be the slack side of the belt. Now if I look at the gear itself, it will have these forces. A normal force acting on the gear tooth will have two components, one in the radial direction, another one the tangential direction, or the one which is tangential to the pitch diameter. So looking at the equilibrium of the gear, we have these forces. I've said we have a normal force which acts at an angle 22 degrees to the vertical. That is, if it is a 22 degree spar gear. If it is a 20 degree spar gear, then it means the tangential component with the normal force will make an angle of 22 degrees in this particular scenario. Then we have also a radial force that acts on the gear, and this is how it will look like. Now if I also expound more, if this is a pinion which is a driver, the pinion is driving gear C, this is C which is driven. So if I consider a pinion rotating, so that gives a vertical downward tangential force. If it rotates in a clockwise direction, then it means the driven gear C will rotate in an anti-clockwise direction. So if I put my tangential force, the tangential force is going to be tangential to all the pitch circles of the two gears. This is the pinion, this is the gear that we are driving. Then this is mounted on a shaft whose dimensions are to be determined. Then the normal force will act, so it comes like this. So when it comes like this and this moves like this, then the normal force will act in that particular direction. Then the tangential force act downwards and the radial force in the horizontal direction, and it will be perpendicular to the axis of the shaft. So considering the equilibrium of the pulley, first of all, we will know that for us to get torque, remember torque is always a turning moment, and it will always be the product of the perpendicular distance and the force itself, because we have this pulley turning, but we will turn due to a tension as a result of T1 minus T2. The net tension in that belt is the one that is going to cause turning of the pulley. Then since it is turning along the distance, the perpendicular distance from the turning point of this force, of this pulley, the force causing it is T1 minus T2, then the perpendicular distance is RD from the turning point, then that torque will be T minus T2 times RD, which is the radius of the pulley itself, and that will equal to torque. So we are provided that the ratio of the tight side to the slack side is 3 to 1. So if it is like that, I'll have T1 divided by T2 equal to 3 out of 1, and 3T2 is equal to 3T1. We are provided that T1 is 3000 newtons, and therefore given this information, I'm able to get T2 as 3000 divided by 3, and this will give me 1000 newton force. So what does that mean? It means we are able to get torque. We say the torque is T1 minus T2, and therefore we have already gotten T2, so I will just substitute in my value. I know RD as 0.4, and this will be 2 times 1000 times 0.4, which gives us 800 Newton meter. That's the torque, and this torque is going to be the torque transmitted from, first of all, the pinion to the gear to the shaft, then to the pulley itself. So the torque at gear C is the same as the torque at the pulley D. So we need to analyze the forces acting on the pulley. Therefore, we have horizontal forces. So the horizontal load on the pulley D is going to be due to the tensions. So if it is rotating around this point, then we know it is being acted on by T1 and T2. So the radial force will be T1 plus T2, and this is going to be of course I'm resolving forces in the horizontal direction. So in this direction I have T1 plus T2, then this will be 1000 plus 3000, and that gives you 4000 newtons. Then the vertical load on the pulley is we are calling it RDV, and this is going to be the weight of the pulley, because there is no other vertical load on the pulley other than its weight that is given in the problem scenario, which is 2500 newtons. Now when we consider equilibrium of gear C, we know that according to this diagram, we have these forces FTC and Fn, the normal force. They have an angle of 22 degrees in between them. Then we have another force in the radial direction, which we are calling FRC. So when we look at that geometry, we will find that FRC is equal to Fn sine 22 degrees. But we know, of course, we have been also provided that T, which is the torque transmitted by the gear, will be as a result of the tangential force times the perpendicular distance from the turning point. The turning point is at the center of the circle, and therefore from where this force acts to the center, it will be RC, which is the radius of that particular gear. And therefore, torque is equal to FTC times RC. FTC is going to be calculated in this way. We already know the torque and we know the radius. Therefore, FTC, which is the tangential component of the normal force at the gear meshing, is going to be 2666.67 newtons. Then from that particular diagram also, we know FTC is also equal to Fn cos 22 degrees. So Fn will therefore equal to 2666.67 divided by cos 22, and this would give us 2876.1 Newton. What does that mean? It means we are able to get FRC, which is going to be 28, of course, Fn sine 22 degrees, which gives us 2876.1 times sine 22, and this gives us 1077.4 newtons. Therefore, the horizontal load, which is FRC, is equal to 1077.4 newtons, and this is FRC because it is acting in the radial direction, and therefore it is going to be a horizontal load that acts on gear C. Then if we draw a system of forces in the horizontal direction, we can consider this shaft to be like a simple supported beam under action of point loads. So we'll have a horizontal reaction experienced at bearing A and a horizontal reaction experienced at bearing B. The vertical load, the horizontal load as a result of the gear itself is in the radial direction and is 1077.4 newtons. Then the horizontal load is as a result of tension on the pulley, and the tensions are all, the sum is giving us 4000 newtons. So if I analyze my scenario, I need to apply equilibrium conditions to determine RAH and RBH. So if I look at sum of forces in the vertical direction, then upward forces must equal to downward forces, and this is what is giving us. So if I call that equation 1, then I look at also moment equation. The sum of moments about A should also give us 0. And therefore, if I take moments about A, it means I have this force acting in a clockwise direction and this force acting in a clockwise direction, whereas RBH acting in an anti-clockwise direction. What does that give us? It gives us 1077.4 times 0.3 plus 4000 times 0.7, which will equal to RBH times the perpendicular distance, which is 1 meter. And this gives us 3023.22 newtons. If I use this equation 1, I'm able to get RAH, which will be 5077.4 minus 3123.22, and this gives us 1953.78 newtons. Okay, we proceed and we have to determine now the bending moment in the horizontal direction. So at the supports, so the bending moment due to reaction AH is equal to 0. Then the bending moment at CH will therefore equal to, I just go to C. I go to C and look at the bending moment that I would experience. The bending moment will be as a result of this force and that force. But since that will require a lot of multiplication, then I will go to this. So it is the same as RAH times 0.3 or 4000 times 0.4, then minus RBH times 0.7. But let me use this RAH moment because it is simpler for me. So this bending moment at the C in the horizontal direction is going to be 1953.78 because RAH is 1953.78. So mine times the perpendicular distance, which is 0.3, this gives me 586.134 Newton meter. because the bending moment is a product of force and distance. Then I look at the bending moment at A. Of course, this is at the support, is equal to 0. Then the bending moment at D, the bending moment at D in the horizontal direction, of course, we are considering horizontal loads. I will go to D. So the bending moment that I will experience will be as a result of RBH or 1077.4 and RAH. But since multiplying RBH and 0.3 is simpler for me, I will take 0.3 times RBH, and that will be the bending moment at D due to the horizontal load. It will be 3123.22 times 0.3, and that gives me 936.966 Newton meter. Then let me consider vertical loads. If I consider vertical loads, I'm told that gear C has a tangential force that acts vertically downwards, and this is 2666.67 newtons. Then another vertical load acts at D, which is due to the weight of pulley D, and this is 2500 newtons. Now I consider this as a system of forces acting on a simply supported beam, and I need to determine the reaction at A due to the vertical load, then the reaction at B due to the vertical loads. Applying equilibrium conditions gives me upward forces equal to downward forces, and also taking moments gives me RBV. If I take moments about 8, it will be RBV times the perpendicular distance, which will be 1 meter, then times 2666.67 times 0.3, then plus 2500 times 0.7, 0.3 plus 0.4, giving you 0.7. So if I do that, then I will have RBV equal to 2550.0 newtons. Okay, that will be RBV, the reaction at B due to the vertical loads. Then the reaction at A due to the vertical loads will be 5166.67 minus 2550 if I use equation 1, that gives me the sum of forces in the upward direction equaling to the sum of forces in the downward direction, and this gives me 2616.67 newtons. Now I need to also determine the bending moments at A, at B, at C, and at D. At A, this is at the support, and that will equal to 0. At B, it is also the support, and it is also equal to 0. At C, I will also go to C. Here, I go to C. The bending moment I will experience will be as a result of RAV, or as a result of this force and that force. But since this is simpler for me, I will get RAV times 0.3. I will get the bending moment at C. Okay, and this gives me 2616.67 times 0.3, which gives me 785 Newton meter. Then I go to D. D has a bending moment that is as a result, the bending moment expense here is as a result of this force and that force. But since I also know it is the same as this as a result of this force, then I will have 0.3 times RBV for simplicity, because the other one involves a lot of addition and multiplication. So I will have bending moment at D due to the vertical loads as 2550 times 0.3, giving me 765 Newton meter. Then, having determined all these bending moments, my task is to find the resultant bending moment, because I have determined the bending moment due to the vertical loads, the bending moment due to horizontal loads. Then I need to determine the resultant bending moments at A, at B, at C, and at D. So at A, having also known that it is at the support, I will have bending moment as 0, and at B, being a support, is also going to be 0. Then at C, the resultant will be bending moment in the vertical direction squared plus bending moment in the horizontal direction squared. Then I will have the bending moments due to the vertical loads as 785. I square it plus 586.134 squared. I take root, and the bending moment at C is 979.68 Newton meter. That is now the resultant bending moment at C. Then the resultant bending moment at D is a result of also the square of the bending moment as a result of vertical loads, and the square of the bending moment as a result of the horizontal forces, and this would give me the square root of 765 squared plus 936.966 squared, and the bending moment at D therefore will be 1209.6 Newton meter. Now my task, having determined the bending moments, I need to design the shaft basing on the maximum bending moment. Remember, I'm told that I need to determine the maximum bending moment, and I need to determine the diameter of the shaft basing on the allowable shear stress of the material. Now, having determined the maximum bending moment, the one I will take is going to be this 1209.6, because it is the biggest amongst the four. This one is 0, this is 0, this is 9,000 something, then this is 1,000, and this is bigger. So I will take this in the design of the shaft. Of course, if I was given information about the allowable bending stress, then I would utilize this in the design of the shaft. But remember, I'm provided with the information only about the maximum shear stress. So I'll only use the maximum shear stress theory, and I need to therefore determine also the twisting moment, which is torque, is equal to 800 Newton meter as determined above here. Remember, we determined the torque as 800 Newton meter, and this is the twisting moment that we are going to apply in the maximum shear stress theory to design the shaft. So we need to also determine the equivalent twisting moment, which is TE equal to pi out of 16, then tau d cubed. But remember, it is also equivalent to T squared plus M squared. Here, the shock and fatigue factors are considered to be 1. So that's why we are having it as T squared plus M squared. But when given the fatigue factors, then it will be like KT, then bracket squared plus KB M squared. Everything under root. So, but here, since we are not given these factors, KB and KT, then we will assume them to be 1 and substitute them in our equation of equivalent twisting moment, which is now going to be the square root of T squared plus M squared, which is also equal to pi out of 16 times d to power 3 times tau. And this, if I equate the two, I will have d cubed equal to 1.84647, and taking the cube root of this value, I will have 56.9 millimeter. So if I'm given several values of diameter to choose from, I'll go to the one which is close to 56.9 millimeter, and this is going to be 60 millimeter. So it's the one I have chosen. Now in this video, we have been able to design the shaft basing on the maximum shear stress theorem, and we are given the several components that are mounted on the shaft, and these are a pulley and a gear. So this pulley is subjected to horizontal loads, but it also has vertical loads due to its weight. This gear has a downward force, and we also discovered that it has also a horizontal load due to the radial force on the teeth mechanism. So having discussed all what is involved in this, then we can say we have answered the question. Thank you so much for following us.